I stole it. I don't know how you made it. You don't have to tell me, but um, I like that. Yeah.
Sure.
Um, okay, so should we go through what talk about the elephants here? I like them.
Yeah.
Okay. You already had a lot of fun talking yesterday about what we're really doing with RISC-V here. And today I thought I would give, again, following Bruce, um, his ideas, that we're not talking about really how things are done or what the technology matters, but how how the different aspects of people work together. And so it's a, what happens when we have different contributors to technology like research and development and manufacturing, what really happens, the messy realities. So I come from 3.5 decades of data storage, first with Seagate technology, always in the hard disk drive industry. I've been a test engineer all my life, subassembly, solid state recording physics for Seagate, and then IBM wafer fab. That's where a lot of wafer experience here today comes from. Western Digital startups along the way with the quantum mechanical principle called the spin valve. Um, but I've always worked around bringing the science and the technology into real high volume manufacturing and all of the messy realities that ensues. And so the journey when you go from working out your beautiful paper theory on paper with your pencil, it's not a straight line to go into a real silicon fabrication and getting the wafer cut apart and bonded in a lead frame and all that. That's a messy process. And so um, if you're writing your RTL code and your Verilog today, how many people here, show of hands, really have thought about the 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 work you're doing with that bit stream and that Vivado output? Um, how many of you really think about all of the people involved in actually using, producing, 10,000 wafers a month with that? That's what we want to get out today. And so actually, Bruce Rosenblum really came up with this, Anushka. It's not me. The apocalypse of the two elephants. As you get some idea to create a single core or quad core, a Linux chip, whatever, um, you have this dream that maybe it's one or two people, a small group in a research. First, you have what are the three phases of of the ecosystem? There's research and development, there's design engineering, and there's manufacturing. In between design engineering and manufacturing, there's this valley. And so these are two large elephants, two large um, spenders of capital and money um, that in the normal product cycle. Now, in Seagate, I remember we had in a lot of companies, there's usually multiple design teams that switch off. Maybe as a research and development team is working on one aspect, there might be another research and development team that's dormant. Microsoft, I believe, has two sides. That's the Windows 3.1 team and a more GUI aspect. That's why you see differences in how, say, Windows Vista behaves than Windows 2000, just different teams. And so when one R&D team is not in vogue actively working, that other team might be doing more manufacturing, kind of switching back and forth. Um, that's not shown here. And so the idea is a research and development team really only cares about uh, creating the specifications and making sure they're held tightly. not really concerned at all with yield. In other words, the ideal yield is 100%, and if it fails 0, it's a failure. Manufacturing doesn't doesn't really care about specifications, but that there's really a normal curve, a bell curve, or some other distribution. There's some percentage that don't work well or at all, and the idea is to try to maximize how many parts are good, but understand that some are not always good. Some um, some plating, chemical etch doesn't really work well. Some lithography is not sharp and well patterned. There's real effects, and so there's this tension, this conflict that's always going on. Um, and so but the tension is good because there needs to be communication. So plan today is that this they go test in the middle is not a hurdle, a hindrance, a four-letter word, but it's really the bridge that tells how the communication needs to happen. And why are we talking about that here? Well, because RISC-V gives us a beautiful um, approach to make that communication happen. The modular instruction set architecture. Anybody here raise the hand? What are the 6 modularities of RISC-V that you heard about yesterday, Anushka? You should say R, I, S, B, U, and J.
Yeah.
Okay. If anybody, when you go back to whatever you're doing at work or school, all the students listening on the call here, if you learn nothing else from this beside IT, LT, YT, the other thing is I want you in your sleep to recite RISBUJ. Unfortunately, you cannot pronounce it, RISBUJ, because those are the 6 forms.
Yeah.
And that really makes it very helpful. And then I'm going out on a limb here, and of course, I haven't talked to anybody else in RISC-V, but it would be really nice. It's sort of a dream I have, a profile, what that means, a RISC-V profile, is centered around how can we standardize around a good definition of a processor? Um, not so much a profile like the applications profile or the microcontroller profile, but a profile where it just defines our basic core things about how we want to sort of a modular, not a totally consolidated ASIC, but a modular component of just the processor. What should that look like? How little or how many types of interfaces? Maybe an ideal processor profile wouldn't even include a high-speed interface. That could be an outside module, just to keep the manufacturability very simple. So it's not about the tools, not about the tool chains or the schematic captures or the EDA, but it's about getting all the different players socially and in a human sense coordinating with each other. And so one way to do that I've seen work well is for when you're people are in research and development mode, and if you're a team of 2 people like Anushka, you and I, we might be one person. Each elephant might be only one person. Um, when we finish our design, you don't just give the description, your GDS file to someone else and say, okay, we're done, build this. Here's the bitstream file. Don't worry about what's in there. Build it and it'll work. Um, take the time to write some, good, thoughtful, not 1,000-page document, but write some good life support manual. Here's the bitstream, and here's how to start it up. I like to keep, whenever I write a process instruction, again, as a test engineer, 2 things I follow is when you write a procedure, 1 procedure per page. Don't write a book. Save a tree, right? Okay. Um, don't maybe one procedure per page and one step per line. If it takes, can you write your procedure of how to load Vivado in the computer? Try that. Write a write a flow from starting from download the Vivado from the website of Xilinx, um, and write each step only on one line. That means being very judicious and thoughtful with what words you want to use and what words you don't want to use to make it a short. And so a life support manual that's concise and simple yet complete. And that is the beautiful, perfect companion with whatever your output is. My first manager at Seagate, Tom Poliquin, always told our team, our product is paper. Our product is not um, a hardware design or a software algorithm. Our product is the know-how to make that product. And so that life support manual, sort of, I call it, goes with that. On the manufacturing side, realizing that there's failures, when something fails and that that FPGA, that um, RDIX that you've developed there, Anushka,
Yeah.
fails, don't just give it back to your research and development buddies, but give one copy or one piece of the actual failing samples, the scar tissue. And so research and development, and not just give, okay, here are the failures and here's why I failed, but take the time to enumerate and explain. Here is, I I plugged it in, I did this, I loaded that, my computer and system environment, my operating system, I used it on a Linux machine with this version of kernel. You have some good definition of what is the background scope, what is set up. And so the design engineers can duplicate your failure. And if they can duplicate your same failure, that's great. If they can't, now they can go back to you and there's the communication that, hey, it doesn't fail for me, but it failed in research and development. It failed for you in manufacturing. Maybe there's a problem like uh, difference. Research and development is using 220 volt and you're on a 110 volt 60 hertz environment. um, I know that's stupid, but there could be some obvious differences in setup or assumptions being made that didn't communicate well when you got the bit stream that was built for assuming your RAM was so much space in one memory location, but when you put that bit stream in another FPGA, the working RAM is a different size than somewhere else. It's very easy to not get all of the assumptions uh, explicit.
Yes.
And so how to make that process of feedback and feed forward, little icon that you see two people working together, clean room suit and a design engineer, is okay. If it's if one group of students is doing the logic design, like the research and development people, and another group of students are doing the actual hardware wiring once the design is fleshed out, is cross-pollinate them, Anushka.
Yeah.
Wouldn't that's and so get the get as much as the research and development team is happy in the ivory tower of ideal perfection, force at least one or two representatives to every week or more often attend manufacturing meetings, the bloody battles of why the yield is not over 70%, and and actually get the hardware people into the design engineering meetings, uh, going through RTL reviews and all those boring things. And so each side can see what the other's pain has gone through. Um, Yeah, it's in the academic world, I liken this to, I think that this fundamental difference between the two sides not working together comes between what, okay, if you call yourself a firmware engineer, do you are do you find more home with hardware or software? Or said another way, is firmware really belong with software or hardware? In the academic world, you have electrical engineering departments and you have computer science departments. The question, Anushka, where does RISC-V fit in?
It's multidisciplinary.
It fits in EECS, right?
Yeah.
Cal Berkeley, I think, called it EECS. Okay, there's kind of, but these are artificial amalgams that we haven't really figured out. Even at the academic world, we haven't really figured out how to create core curriculum or really a teaching methodology that teaches firmware as firmware being both or neither. And that's kind of a different angle between the whole ecosystem here is not just research and development and manufacturing, but it's both. There's neither. So there's some food for thought, some cross pollination.
Yeah.
And so in part of that, because wafers are expensive and even the time to synthesize a bit stream is not so fast, we create these test benches, or in the wafer process, I call them coupons. I'm not going to make an 8-inch wafer with 3,000 recording heads. And by the way, in my hard disk industry, the wafer is very thick. Actually, the thickness of a of a uh, not a silicon wafer, a uh, um, a ceramic wafer is actually the leading to trailing edge length of the recording head slider that flies on the surface of the disk. So it's a thick wafer, maybe almost maybe a tenth of an inch thick compared to a real silicon wafer. And there's many, tens of thousands of recording heads on an 8-inch wafer. Uh, in in VLSI silicon, the chips are bigger, and so I think there's only a few hundred chips on a wafer. And so we would, in order to test the process, making sure the plating is going wet chemical etch, dry etch, high vacuum deposition takes about 900 or so, maybe over 1,000 layers to make a wafer. Um, we want to test pieces of the process, so we make these small coupons. We call them literal size of a quarter, maybe 2 or 3 inch diameter test samples. Now, it was one great colleague from Joe Smythe from IBM always asked, he was a research and development engineer with a mindful sense of manufacturing. Joe would always question us, are we really in the business of making product, or are we making the world's best test coupons? And think about that. When you're heavily relying on QEMU so you can build everything in a simulator and see it right, are you building the world's greatest product or idea in simulation mode, or are you really building product? And so there's a big danger of you relying upon simulators too much. Um, be careful and judicious um, in that aspect. Um, and aside from that, I like to think about how do we stay healthy. I hope everyone does here, read nutritional labels. Are you mindful of what's in the food that you're eating, breakfast, lunch, and dinner? And think about that same nutritional label here with RISC-V. In other words, how much depth of logic do you have? How much sugar is in that design that you're doing? Are there preservatives that you're using? Um, what, just some fun ways to think about, you know, what you're creating is it bloated and obese? Is there a lot of um, high density lipoprotein fats that are not so healthy? Too many extra routing layers that if you, again, IT, right, taking longer than you think, if you allowed yourself a little more time, not just working out, say, some design model, but giving yourself time to work out in a way that it's object oriented, extensible, maybe you can optimize so it not only fits in to grow in the future later, but it's lean in the sense of not taking a lot of routing space kind of organically. And so that's kind of like a nutritional label scorecard method I thought about. That you know when you're shopping for your groceries in the store, you know you don't have to go overboard understanding everything that went into the farming, the growing of the ingredients that hit the grocery store or where things come from. That you could leave that, give the autonomy to the folks and the people managing that, but just be mindful of what you want and how it's affecting anyone else. Um, and so, like I said, the preservatives might be the bloat or the how much reliance on the simulator tools. If you create some beautiful bit stream that's still dependent or tied to sale type characteristics, is that really necessary? Or is I realize simulators it's a helpful tool in the step, but should the specifics still carry through, or really do you should take more time to abstract or synthesize yourself in your mind what you need to learn from that and take it out of the simulator mode and build it into what you're doing, and so it's well contained. Um, so I put on some more. You'll get the slides. I hope you'll send them around, Anushka. Some different ways to score and you know there's good things that to think about. Let's say simulators. I know a lot of people find them, and I like to use them too. That that you can that you use them as tools, but they don't have to go much further than that. And everybody that I've talked to really has never liked, the idea of test. It's something that in the perfect world when things are working, yields are high and designs are well done. Um, I've heard a lot of it at Seagate and at IBM, Western Digital have always questioned, why do we need the test? The cost of test is okay after every a product is mature and some design is working well, can we lay off the whole test team, cut the budget? Heard that a lot. And test becomes that four-letter word that I'm sure we all know. um, but it really can't be done because there's even the best design is going to fail later, even when some tiny aspect changes, and that manufacturing elephant is going to find even the tiniest crack that we didn't expect would be there. And if we don't keep breaking it and we don't keep testing it, there's different aspects of tests. There's in situ tests that don't affect change on the product. There's destructive tests, that maybe you want to have some sampling of your product. Um, Take something out of the line, test it, see if it works, and then throw it away. You wouldn't want to put it back in the line. Electrically, um, I use, there's wafer probing. I use something called pogo pins. You might have seen those little spring plunger electrical contact probes, and those are very nice. You know, one of our groups had an edict that if you're going to probe a physical device, you never probe the customer aspect, the business end of a connector, because every time that you have a insertion and removal, you have some mechanical fatigue, you weaken your spring connectors. And so maybe you want to make use of a test equipment with pogo pins that probes the back, or maybe if on a wafer level, you never want to put your tungsten probes on the wafer because you're going to get some scratching going on. So you touch in an area, you probe different areas if your testing is not really non-destructive and in situ like you like it to be. Going too fast? Should I continue or pause here for any question, Anushka?
Any questions from the audience? So no questions as of now.
Okay, okay, I'll keep, yeah, you'll send one. Um, so the RISC-V is great because it's sort of an open source silicon, right? There's a maximal reuse. What does object oriented thought really mean? It's um, it, you encapsulate things that are related and you separate things that are not, and that's how you can reuse whatever class or or object that you're working on. And RISC-V allows exactly that same kind of separation. And by separating in in a thoughtful object-oriented way, you you don't have, once you work out something and it survives fab, it has good yield, and the life support manuals are well understood from research and development, you can reuse those that evolved learning. In other words, you're not reinventing your gate. You're not working out the same kind of ring oscillator every time. You're just doing a lot of copy and pasting. It's like, okay, that clock tree implementation is already done. I can just bring it in here. And if it's well thought out and it doesn't have a lot of assumptions, what is an API? An application programming interface. Isn't that it's at the interface between research and development and manufacturing, or the other way around. Uh, an API is nothing more than promises that you need to keep when somebody else uses your stuff, and on the other side, promises that need to be made. So an API is a handshake between two people. Um, and so there's this nested modularity of RISC-V that's really important. RISC-V allows, okay, yesterday you probably in your, you know, many people of this wonderful discussion that you put together, I'm sure you saw the extensions where RISC-V allows us to encapsulate behavior that belongs together and separate behavior that doesn't. We have the M extension. What are the, okay, I want to hear some voice. Give me 3 instructions of the M extension. There's more, but name 3.
Yeah.
Wait a minute.
3 instructions.
Give me 3 instructions of the M extension. See how you learned yesterday, anything. How about multiply?
Yeah.
How about divide?
Yes, yes.
And what's the third?
Yeah.
It doesn't mean remark. What is rem? It's not remark. If you think in basic, right? You know, or is it REM is a comment, right? In basic. Remainder, modulus, modulo, right? The M extension, implementing the M extension is very easy. It's not a lot of circuitry for that. that aspect of to implementing M extension of your processor. You have a multiplier, you have a divider, and you have a remainder. The maybe if you don't if you want to do an M extension without that difficulty, you might leave it out. You can just handle multiply and divide without any remainder at all. You can put that kind of M extension. But those are three. The atomic extension has your AMO and your load LR and SC, what? Load reserved and store conditional. Your base I extensions, that's about 37 instructions that you pretty integer only that operations that you can do everything with. You don't need anything but the I extension, your relative arithmetic, your logical instructions, branching, stuff like that. But with those extensions, what I want to say here on this slide, I know it's got a lot of words here that I'm not reading, but you can read faster. Underneath the layer of the abstraction of the extension is that other layer that is these six forms, the RISBUJ, that I want you to sleep with and live them and learn them and use them. Those are the six forms that kind of like Lego blocks that you can build everything from. And the fact that there are six and only six and no more than six, actually, I lied. What I did not write one of the seventh instruction form. What is that? Anyone? RISBUJ. What's missing? Hmm? You know, Anushka? Okay. Um, think RV64 or how about R4? Okay. The way that these six forms all work with one or two um, source registers and a destination register. Maybe that in the case of the I and the U and the J, there's immediate constants of either short 12-bit or long 20-bit forms. What's not shown here, the seventh instruction form, or the 6.5, is R4. It's a, it's a register instruction form that takes 4 registers, not 3. And that's handy for in the rare case if you're having like a 64-bit or greater uh, data that you want to access, the R4 type in the rare case that you need to in that one instruction get down and decode and get into your pipeline uh, both the low 32 and the high 32-bit. But I I leave that out, and we can leave that out as a special case of R. So just know that in fact, it would be a very good, I haven't done this, but I have an idea. Anushka, I put to any of the students here at Charutar University, um, write, make a little matrix or write down on paper, let's say take the M extension and go through each extension, each instruction of each extension on, say, columns, and write down the which or one or more of the RISBUJ instruction forms are used in that extension. That would be a very interesting picture. Now, why are we talking about this in manufacturing? Because all we have, all you have to do in manufacturing, again, like I said, going back to um, this slide here, when you're in the grocery store and you're shopping for your groceries, you don't really pay attention to the fields or the farms that are making those plants or milk or whatever they're doing. That's already done for. And the same thing here, using the idea of these instruction forms, you can once you design in a well thought out abstract way the circuitry for that R type instruction decoder and pipeline circuitry, and the branch logic and this branch prediction, that that circuitry is pretty much designed, done. You really don't have to, if you did a good job, you don't have to touch it again or any other group. You can copy and paste that circuitry. So you have these little Lego blocks, these 6 Lego blocks that you can move around and rely upon, and they've already stood the test of time. They've already stood the um, the yielding and being worked out by manufacturing. Do you rely upon some unmanufacturable narrow line width that's going to get a lot of rat bites and electromigration in the process, with a lot of like overly complicated, bloated, sugar like um, um, branch prediction handling operation? Or have you thought out making the circuitries manufacturable and nice and well organized? But you can, what I'm trying to say is that the RISC-V circuitry design layout, fab yielding experience, all the scar tissues have been worked out and understood as done. You can tie them together in a modular, snap together way, and so there's a sense of freedom that you can really add, evolve later on. And so again, I'm sure you've explained what RISC is. It's reduced instruction set computing. You covered that yesterday, I'm sure. And we created the five aspect was in 2010 at Cal Berkeley with Andrew Waterman, Dave Patterson, Yunsup Kriste Asanovic. And that it interesting to go back to look at what is RISC-V. How about what is RISC-III? Actually, RISC-I, RISC-II, and RISC-III have some very interesting color names. I can't remember off the top of my head, but that's a little side example. Um, Look at the history of what are the RISC-I, II, and IIIs in there. And so you don't, and I think I read somewhere about one of the faculty of some curriculum at Charutar University there in your SAT is grammar. I came across people talking about grammar. Is that right, Anushka? And I like to think about ISA, the instruction set architecture. ISA, isn't that just a grammar like any human grammar? And instructions are your verbs, your actions, and registers are the nouns. So you got nouns and verbs and grammar. You talk the language, and to RISC-V core, their instructions and registers, and your grammar is the ISA and the assembly language that you're writing. And there's not a whole lot of verbs. There's only about, I think I counted 82 instructions total between the I extension and a few others. And it's easier to learn and use a language if you don't have a lot of verbs. How many instructions are in Intel x86? A lot. Yeah, okay. Okay, you got the point. Um, and to remind you about, okay, what are these 6 forms? I'm sure you've seen this already, right, Anushka? You got the verbs. Okay, now, so RISC-V, if you close your eyes, you wake up in the morning just before you go to sleep as your nightly prayers are, add to the nightly prayers some remember RISC-V. Okay, short immediate, long immediate, where, okay. Um, Show of hands, anyone know the difference between U and J? Okay, look at the U type. There's a 20-bit long immediate in the U type. And look at the J. The J form is also a 20-bit long immediate. Now, the J type immediate, the pieces of those 20 bits are kind of scrambled up, but they're still 20 bits. So in your decoder process, if you're, again, your circuitry, does this mean that you only need one type of circuit that you need to design and teach manufacturing about? You can put U and J together. Anybody? Do you know why U and J are not the same,
They're
Anushka?
not the same.
Think about what they're related to. The the U type is pretty much the Louis, the load upper immediate, is a number that is absolute to the memory space without any knowledge of where the execution flow is. There's no reference to the program counter. The J type instruction is the 20-bit immediate that's getting internally the circuitry of the J extension is adding in the program counter. And so that's where you have the different, look at the difference between I can't always pronounce it, AUIPC, add upper immediate program counter. Compare that with the LUI, load upper immediate. Look at those two instructions and you'll see the difference between U and J. And look at the circuitry. Same question between S and B on the short immediate side, the 12-bit. Again, the S type has 12 bits. It has um, bits 5 to 11 over on the high end, most significant end of the instruction word. And then you have the 5 lower bits kind of next to the opcode. You put those together, there's 12. And that's exactly the same framing as the B type form. Again, the difference is the S type form is going to be a circuitry that is connected only to the abstract base that you would use for a store operation. But the B type form is going to internally add in the program counter information. And that separation, that's, I want to point that out because this beautiful diagram doesn't show that bifurcation, but it's necessary. And so that's a good question. Why do we need to fundamentally think about um, teaching manufacturing how to yield 6 forms instead of just 4? Because certain operations like branches need to know where in the program counter flow they're being executed, or or the um, or the long immediate uh, where you're doing a far jump or far branch to. You've seen that. And so this is the picture of, like I said, how the Lego blocks stack together. So inside here, each one of these blocks is built of 6 or less sub blocks. The RISBUJ are kind of in here. Maybe that's the coloring that you see here. And so stand on the shoulders of the people that have come before you. Um, and think, if you're designing something, make the lives of the people doing the jobs in manufacturing easier. Uh, and again, when you're manufacturing them, don't stack them together in ways that are, make research and development folk unhappy. And again, you can really, really impress the boss if saying not only your estimation of time, IT, LT, YT, it takes longer than you think is correct, but when some question or demand from marketing comes in, we need to make a 5-core processor. You've already made your design so modular, so well worked out, says, oh, I don't need to do any work because all we have to do is flow a switch. We can use the same tools, modularity and compatibility, adhering all of the standards were followed. We already support this and we never thought about needing it. In other words, planning, if you want to think about 3 variants of something, you would use 2 bits and you would have 1 extra possibility because 2 bits gives you 4 combinations. If you use you only needed to have 3 aspects of some control feature, might give you a little bit of leeway if you will allow or arrange some multiplexing to give you not 2 bits, but 3 bits. You could have 8 levels. Now you can support a lot more. So in the future, you've already added or 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 thought enough ahead of time to allow for that possibility. And so manufacturing doesn't have to relearn any scar tissue, and research and development doesn't have to uh, add or give you any new life support manuals back and forth. You already thought about the future, not even knowing what the future looked like. Um, and so I know a lot of people are going to criticize me really heavily. I'm a text person. Do you use latex, Anushka? Anybody
Yes,
here?
sometimes.
Sometimes I use in the Thai. I read and write the Thai language. I use XE LaTeX, beautiful, and and so can we think about it's this? I had an idea also. I call it a technology humanity metric that you know we 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 spend all our time with wonder next versions, but the one thing that your manufacturing elephant hates is change. You know, it's change is good, but change is dangerous. And so think about Windows gets an update every week. How often does your smartphone update? Google Android is terrible. Every I think it's like at least 3 times a week, I see 12 updates of apps. Um, Text hasn't changed 2 versions in 40 years. Don Knuth did a great job. And yet, not not that it's not dead. Every doctoral student does every one of their dissertations with text. It's pervasive, it's out there, it just hasn't changed. There's packages that are added, just like extensions in RISC-V that are always added, but the core hasn't changed in 20 years. I really like how Don Knuth made his version. Every time he changes the version, he adds another number of the non-repeating decimal of pi onto the version number. Um, can, so RISC-V gives us a chance to be the techs of silicon. And so there's this picture I think about. There's no data here, just kind of my feeling is, look at the 555 timer. Okay, how old is that? The LM555. It's cheap. Okay, it's it's in the sense of a humanity score, ecological, and there's some ecology aspect because if it doesn't change a lot, it doesn't consume a lot of resources, right? What are the 3 R's? Reading, writing, arithmetic. How about reduce, reuse, and recycle? And so this metric is what's the ratio between the human impact and how much it has damn thing has churned. Um, Windows is pretty bad. It's you see. So it's more bang and sanity for the buck. Put into sanity, more bang and humanity for the buck. Um, and RISC-V has a good chance. Probably, I think RISC-V should be to the left of Linux, but um, that's some we can. This would be good to debate. Um, and so come back to this not a formal spec, this idea, wholesome way to think about RISC-V cores that don't, do we really want to bring, put everything in the kitchen sink uh, into a core profile, or do we want to be modular about it? I didn't have time to make the slide, Anushka. Let's see if we can think about this. Does anybody know what is a component stereo system? Anushka, do you you know what I'm talking about? Maybe at home is how many people still have record players? you have a components audio system. You have your amplifier. You have your cassette. How many people have stuffed cassette decks, right? You have your cassette deck, your DAT, your tape decks. Okay, I still have an open reel deck. Um, your turntable, um, modular pieces. What connects them? The standard of the RCA jack. Okay, and that allows a connection between the modular pieces in a very standard way. Again, open standard. Um, Instead of the integrated unit, which maybe you buy one completely integrated modular 4K high definition TV with uh, an operating system and DVR. Everything is self-contained. Doesn't give you a lot of freedom if you want to upgrade or change from like a DVD to a Blu-ray player. If everything is all contained and integrated tightly, good for good for high profit manufacturing, private, okay, corporate capitalism. Bad for the earth and the consumers for freedom. Um, it's, it's if something fails, then pretty much have to throw it away and buy something new. Okay, do you want to design for reusability or do you want to design for profit? So think of, can we, wouldn't it be neat? I don't know. I like what I see happening with the Shakti processor and other aspects that going on right now where you are. Can we sort of get a modularity sense or in mind that, again, the idea of a profile that lets us think about a good formal well-designed five stage uh, multiple issue out of order processor, but is lean on the peripherals, doesn't have Wi-Fi, doesn't have Bluetooth, doesn't have high speed uh, PCI interfaces. That's all extra. In other words, think about the gestalt of the power, performance, and adaptability. And so, how can that modular processor be a very good, well-defined clock path, clock tree, good power buses in management, interface, simple enough interfaces that you can describe with a piece of chalk on a sidewalk. And then that you could we could have P profiles of simple processors, different, very complex processors, but more the line of, remember how pervasive the Z80 was? The Z80 is was a microprocessor. Again, think about microprocessor and microcontroller, and go back to a little bit less integrated SoC, system on chip, and more modular. That's an idea. And so I have this vision in mind that um, have just the basic okay, what would be a good set of basic standard interfaces? Maybe of course UART, bootloader, startup, easy to design, very well thought out, easily manufacturable and testable, um, uh, asynchronous clocks, all worked out. SPI, I2C, some timers. That's it. And then all the other necessary and important peripherals are outside of that, not put together. And so it becomes easy to verify, easy to validate, just because you reduce the scope of what something needs to have and what something must have. Again, that goes along what maybe what design for manufacturability, design for usability and freedom might look like. Okay, um, so enough here. So let's throw out a question here. Um, are you testing the reality of what your customer gets or what you wish we had? How many how many students have put in temporary hooks or test modes? Are they necessary? Do you want to, how often do you rely upon or you find it's important to um, work in lots of backdoors to make things easily testable, special test modes? And how much do you feel that, okay, I don't, when I'm working and testing this concept, I don't want to do anything different than the front door like everybody else walks through? Any thoughts? No right answer. No wrong answer either. Controversial, right, Anushka? But it's important. I've always gone through my test engineering using the public, using only the aspects of the API that that the customer sees. You know, on the software end, it means, are you designing so that you can connect into some secret special ways with a special DLL and hook into the code that you're linking into? Or are you test harnessing the code that you're writing totally at a scripting level, and you, to test it, you either manually type on the keyboard feeding input to your code, or use some bash piping characters put in a small script loop and literally uh, build robots that act just like standard input feeding stream, whether it's a human typing on the keyboard or something putting into a standard in, but you're using the same entrance point into the box you're testing. I've always done the latter. Um, but I realize sometimes a hidden test mode is good, because we shouldn't feel guilty about using them. But if we learn something from hidden test mode, we really have to go the extra mile. And in other words, if we find some special functionality is important that we're relying upon, uh, is it really important enough? Maybe we need to um, make it um, uh, real, exposed, and a fundamental part of what we're doing, or we, or can we um, uh, learn from what we're doing with that special test mode
Yeah.
in another way that we maybe it would be a little more laborious to use only the the uh, the publicly promised. What is an API? It's a promise is made and promises kept. Do we want to make some special promises only for you, Anushka, to make our lives easier in test? Or do we want to go through a few less, a few more laborious steps so that we can we can abide by only the promises that I make to you, John, over there, uh, in in an easier way? So next, think about this when you're um, working on uh, working on something. And then the next in manufacturing, I know I'm not a never been a big fan of buzzword these Six Sigma and total quality management and lean. Never really understood what lean and black belt and all that. Um, are they necessary? I mean, there's a lot of money. I mean, this when you talk about the manufacturing elephant and the research and development elephant, the manufacturing, these are there's some big money, right? There's certifications, there's money, there's training, there's a lot of money in here. But is it, of course, it must be necessary, right? But is it practical? Is it necessary that, or is it just bureaucratic? Do you, what's your feeling on it? You know, uh, prove me wrong and that it's, tell me it's really necessary. And maybe instead of design for manufacturability, uh, sort of thinking more in the sense of this system of uh, life support manuals done proactively from research and development elephant side, and scar tissue report and handback feedback from manufacturing side, that could be more of a evolutionary perspective of what this alphabet soup looks like to me. Uh, so, is the jargon necessary? That's the next question. You know, yeah. Uh, Something to think about here. And then your turn here. I guess you know, don't be shy. Um, it's no dumb question. I like what I see in your yeah Charutar. Just learning the difference between tar and your um, the science and technology aspect of Gujarat. Great place, great company, and yeah, I hope to see it. And in return, I hope to see any or all of you out at Santa Cruz too. Yeah, beautiful. You wouldn't want to go to any other university, you know, to study and work in a nestled in a redwood forest up in the hills overlooking Monterey Bay. All you need to do is see fog rolling in one evening